Welcome to the second video of the third week. It's part of the series on binary codes and tools complement. Now, in this series, you will hear about binary codes. We will talk about how digital systems interpret user inputs. And we're also going to focus on some specific binary codes, the most prominent ones being the binary coded decimal, or otherwise called BCD, and the American Standard Code for Information Interchange, otherwise known as ASCII. Now, part of this series is a gray code, but we're going to focus on that on a separate video, which is going to be the last one for this week. So, how do digital systems interpret user input? So, let's focus on this example. We got a keypad and a user types 2. That appears on the display. When the user types the plus button, that information goes through the digital system adder, and then the user types 5. When the user types equals, well, by pushing the equals button, the result will appear on the display. But that was an easy example, and it cannot be generalized. And this is because both 2 and 5, they are easy to convert into binary numbers and easy to add. By coincidence, the result of adding both of the input streams by the user, both of them can be added, and the straightforward result is 7, which is correct in this case. Now, let's see what happens in this example. The user enters 2, which is encoded in this binary format, plus 5 and 3. Now, obviously, the user wanted to type 53. If the user hits the equals button, the result should be 55. However, if 5 and 3 are considered the same bit stream, and you put one next to the other, well, if you convert that to the decimal system, the number would be 83. And that's wrong. What digital systems do in order to add is that they read each digit at a time, and then they associate the digits to a certain combination of n-bit strings. In other words, an n-bit string which would be correct and not a wrong representation like in this example over here. So in order to see how this is done, let's visit the binary coded decimal code. But before we do that, this table is for your own information, just to show you that besides the BCD, you've got other possible codes available out there. We're going to focus on the BCD because it has some nice, interesting properties. And it's also nice for educational purposes. So let's focus on the mapping between decimal digits and BCD representations. Take a look at it. The BCD code stops at here. Now, what happens from here on? Let's understand that via an example. Suppose that you add 4 and 9. The result is 13. Well, you don't have 13 here because BCD stops at 9. Now here is the secret. If you add them, the result in binary will not be part of the BCD code because it exceeds here the part of the table that you have the BCD values. Now you can do one trick. You can add number 6 in BCD representation. In other words, you can always add 0, 1, 1, 0. And the result automatically gives you what you want. Let's do the addition together. 0 plus 1 gives you 1. 1 plus 0 gives you again 1. 1 plus 1 gives you a carry and a 0 as a result. Now, the carry plus 1 over here gives you again a 0, and because of an overflow, if you can call that an overflow, you get the 1 as the most significant bit. Now, if you go back to the BCD table, you will see that the first 4 bits are indeed mapped to 1, and the later 4 bits are indeed mapped to 3. So 13 is the combination of these two digits in BCD representation. To recap, the trick with BCD is to always add 6 if you're exceeding number 9 as a result of an addition. Now, BCD is useful and is mainly used for storage of decimal numbers. So, after seeing how we encode numerical characters, let's see how we can encode all possible characters. Let's focus on ASCII, which stands for the American Standard Code for Information Interchange. Take a look at this table over here. Besides all the well-known characters to you, there are codes for special characters like delete, like tilde, and all these special characters over here. Now, the purpose of showing this is not to focus on the details, but to understand how the ASCII code works. Now, the ASCII code uses 7 bits. This is the bit stream. It starts from the 7th position, which is bit 6, bit 5, bit 4, all the way to bit 0. In order to locate where the desired string lies in the table, you need to focus on the first 3 bits and use them as their column. And then the rest 4 bits indicate the row. Let's understand that better with an example. Let's take the character A. Now, character A is in this position in the table. This means that the 3 most significant bits should be 1, 0, 0, or in hexadecimal, 4. Now, if we turn to the row number, it gives us the next 4 bits, the least significant ones, which is of course mapped to a hexadecimal equal to 1. So the hexadecimal code for character A is the one that you see over here, or otherwise in binary format, it's this one, those 7 bits. Okay, now here comes a nice question. What is the number that you would subtract from the ASCII code of a decimal digit in order to obtain its correct binary representation? In other words, if you turn to the binary codes according to the ASCII coding system of any of these digits, which number you would subtract in order to get the actual number represented by the digit? I suggest that you hit the pause button and think for a moment. Those of you that thought it's the character 0, you're absolutely correct. What you actually need to do is turn here, find character 0, find its code, and then you know that this is the binary representation, this is the hexadecimal one, and this is the decimal one. So by subtracting number 48, you always get the actual number. As an example, try to subtract number 48 from the ASCII code of 0. That would be equivalent to subtracting 48 from 48, which would give you 0. Now, because the ASCII code is incremental, The decimal number for 1 is 49, so by subtracting 48, that gives you 1, and so forth.